Complete and exhaustive overview of entropy. Entropy is a versatile and deeply fundamental concept that spans numerous scientific, mathematical, and philosophical domains. It is often referred to as the measure of disorder, randomness, or uncertainty, and it has unique interpretations depending on the context. Below is a comprehensive breakdown of entropy, its theories, equations, applications, and philosophical interpretations. Historical development. Introduced in the context of thermodynamics by Rudolf Clausius in 1865, entropy was initially used to describe energy distribution in systems. Extended to statistical mechanics by Ludwig Boltzmann, who linked entropy to microscopic states of a system. Later, Claude Shannon redefined entropy in the context of information theory. 2. Entropy in thermodynamics. Thermodynamic entropy is central to understanding heat, energy, and work. It provides insight into the feasibility and spontaneity of processes. Key definitions. Clausius definition: S equals delta Qrev, T, where delta Qrev is the reversible heat transfer and T is the temperature. Change in entropy. Delta S, delta S, delta S, delta S equals Qrev, T. The second law of thermodynamics. Isolated systems. Entropy tends to increase in an isolated system, moving it toward a state of equilibrium. Delta universe is greater than or equal to zero. Spontaneity. A process occurs spontaneously if it leads to an increase in total entropy. Irreversible and reversible processes. In reversible processes, entropy remains constant. In irreversible processes, entropy increases. Thermodynamic applications. Efficiency of heat engines and refrigerators. Eta equals 1 minus T. Sealed thought, where eta, efficiency, entropy plays a role in determining maximum efficiency, Carnot efficiency. 3. Entropy in statistical mechanics. Statistical mechanics provides a microscopic interpretation of entropy, connecting macroscopic thermodynamic quantities to the behavior of individual particles. Boltzmann entropy. S equals kb ln omega s, entropy kb, Boltzmann constant, 1.38 times 10 to the 23 J, K, omega, number of accessible microstates. Key principles. A system with more microstates, omega, has higher entropy. Entropy bridges thermodynamic properties, like pressure and temperature, with atomic or molecular behavior. Partition function. Entropy can also be calculated from the partition function, Z, in statistical mechanics. S equals kb ln Z plus kbt partial differential lane Z, partial differential T. 4. Entropy in information theory. Entropy was redefined by Claude Shannon in the context of information and communication as a measure of uncertainty. Shannon entropy formula. H, x, equals minus I equals 1 np, xi, log bp, xi, h, x. Shannon entropy of random variable xp, xi, probability of outcome xi b. Base of logarithm, commonly 2 for bits. Properties. Maximum entropy occurs when all outcomes are equally probable, p, xi, equals 1, n. Additivity, for independent systems x and y, h, x, y, equals h, x, plus h, y. Applications. Data compression, guides optimal encoding strategies. Cryptography, measures the randomness in encryption. Machine learning, entropy helps in feature selection and decision tree splitting. 5. Entropy in chemistry. Entropy is pivotal in explaining chemical reactions and equilibrium. Entropy change, delta S equals delta H, T delta H, change in enthalpy T, temperature Gibbs free energy. Entropy determines the spontaneity of reactions via Gibbs free energy. Delta G equals delta H minus T delta S. Delta G less than 0, spontaneous reaction. Delta G greater than 0, non-spontaneous reaction. Chemical examples. Dissolution of salts increases entropy as ions become more dispersed. Combustion reactions involve a significant increase in entropy due to gas formation. 6. Entropy in cosmology. Entropy plays a significant role in cosmological theories and the understanding of the universe. Black hole entropy, S equals kbc3a, 4, proposed by Bekenstein and Hawking, relates entropy to the area, A, of a black hole's event horizon. Heat death of the universe predicts a state of maximum entropy where energy gradients disappear and no work can be performed. Arrow of time. The second law of thermodynamics implies that entropy increases with time, giving a directionality to time, the arrow of time. 7. Mathematical and philosophical perspectives. Mathematical properties. Non-negativity. S is greater than or equal to 0. Additivity. Total equals SA plus SB. Extensivity. Entropy scales with the size of the system. Philosophical implications. Irreversibility. Entropy explains why natural processes are irreversible. Order and disorder. While commonly associated with disorder, entropy is more accurately a measure of energy and information dispersal. 8. Practical and multidisciplinary applications. Physics. Analysis of engines, refrigerators, and phase transitions. Chemistry. Reaction spontaneity, equilibrium studies. Information science. Data encoding, encryption, and storage. Ecology. Energy flow and biodiversity studies. Machine learning. Feature selection, optimization techniques. Economics. Models for uncertainty and resource allocation. 9. Analogies and simplifications. Entropy as disorder, often used in a qualitative sense, but not entirely accurate. Entropy as energy dispersal, describes how energy is spread across available states. Entropy as uncertainty, especially relevant in information theory. 10. Conclusion. Entropy is a universal concept that bridges macroscopic thermodynamics, microscopic statistical mechanics, and abstract information theory. It not only explains the direction of physical processes but also connects various scientific disciplines under a unified framework. Understanding entropy is crucial for grasping the underlying principles of energy, information, and the natural evolution of systems. This exhaustive note encapsulates all known theoretical and practical aspects of entropy across diverse fields of study.